Polyprotic acids. In this video, we will define polyprotic acids and learn how to calculate their pH, as we did with monoprotic weak acids and bases. First, let's break down the word polyprotic. Poly, meaning many, protic, meaning protons or hydrogens, means that a polyprotic acid has multiple hydrogens that can be removed. For example, we can look at H2SO3. If we remove one hydrogen, we still have another one that can be removed. So let's remove that one as well, leaving us with this. Notice each of these hydrogen removals has its own Ka. They do not come off at the same rate, and this needs to be accounted for when we do the calculations. We'll talk about this at the end of the video. Before we start this problem here, we need to have a bit of a map of where we are going, since it's a bit of a long problem. We'll start by making an ice chart, as we normally would, for just the first hydrogen being removed. Just like for normal weak acids, we fill in the initial value and use Ka to solve for X and solve for our equilibrium values. From here, we can fill those equilibrium values from the first ice table into a second ice table as the now initial values. You can then fill in your variables again, an equilibrium equation into the Ka equation, now using a second Ka, to solve for the variable and therefore your equilibrium values. Now you'll have all the information that you need to write down the answers. You'll just have to be careful to keep your accounting straight. Before you're continuing, you may want to pause and see if you can do this problem using the map above first. Then when you get stuck, play the video until it fixes your problem, pause, and continue. You theoretically have all the needed skills to handle this problem now that you have this map. Let's start out with our first ice table. We fill in our initial values of 0.25, 0, and 0. We fill in our variables for the change, and now our equilibrium formulas. From here, we can fill into the Ka equation using 4.5 times 10 to the negative 7th. Because our concentration divided by Ka is well over 1,000, we can estimate that the assumption will work and simplify our equation as shown here. Now we need to quickly check that our assumption was valid by taking the X that we solved for and comparing it to the 0.25. Or in other words, solving for the percent ionization. We do this and we get 0.13%, well below 5. So we can continue with our problem. We now have our value of X, so we can solve for our equilibrium values for each species. These equilibrium values can now be taken and filled into a second ice chart created from the second equation, removing the second hydrogen. First, we'll take our values from the previous slide and fill into our initial value of our second ice table. We put in our variable just like before. I typically like to use the letter Y or some other letter, just to keep everything straight. From here, we'll solve for our equilibrium and we fill into Ka, now using the 4.7 times 10 to the negative 11th. Now something interesting and extremely helpful appears. We can look at our concentration divided by Ka and see that it is well over 1,000. And so our assumption should be valid. But now we can make this assumption twice. If Y is very small in comparison to the 3.35 times 10 to the negative 4th, then it won't matter whether we are adding or subtracting Y. It will still not significantly alter the number, making this equation reduce down to this, which reduces down further simply to Ka equals Y. And you'll see that this is a relatively common occurrence in these polyatomic problems. Now, like always, we must check that our assumption is valid. We put Y over our initial value of HCO3, giving us this incredibly small number, validating our assumption. We can now solve for the equilibrium values of the species. And all that is left is to sort through the work for our final answer. Here I have reduced down both ice charts so that they fit into one slide so that we can look and see where all our answers came from. Our initial value of H2CO3 was 0.25, and we subtracted X from that. However, that didn't appreciably change the value. For HCO3 and H+, we had 3.35 times 10 to the negative fourth minus Y, and 3.35 times 10 to the negative fourth plus Y. But the Y did not appreciably change the number, and so both just came out to be 3.35 times 10 to the negative fourth. For CO3 2-, this all came from the second ice chart and was simply 4.7 times 10 to the negative 11th as shown on the previous slide. The last one we still have to solve for, and that's the concentration of OH-. Since we know the concentration of H+, we can find the concentration of OH- by taking the Kw divided by AH+ concentration. Now let's talk about one thing that I've used already but did not actually talk about how I was able to do. In the previous example, we needed to decide which Ka to use in each ice table. How did I know which to use in each circumstance? Well, first, since the H+ that is removed first will be coming from a neutral species, this is much easier to remove than the second hydrogen, which is already on a molecule with a negative charge. And so H2CO3 is a much stronger acid than HCO3-. And therefore, this first deprotonation step happens much more often and has the higher Ka associated with it. And so the higher Ka matches with the H2CO3, the lower Ka matches with the HCO3-. In this video, you have now learned what polyprotic acids are and how to do calculations involving them. We have also discussed how to identify which Ka relates to each deprotonation